Right. Today we'll be doing a summary lecture. So I've tried to sort of go through all of our learning goals and look at the ones that I've designated as no, and I'll try to do a summary through all of those. Of course, the be familiar stuff is also important with regards to an exam, just being familiar with different kinds of valves and stuff like that, but it's the things that you're supposed to know that we need to try to do a summary of right now, and I'm a bit unsure if I'm going to manage to do it in just 2 hours, but I'll try. It's quite a lot of stuff to go through. So some of the first stuff that we went through was the fact that we were going to be able to explain throttle points and cavitation and be able to distinguish the properties of hydraulic fluids based on viscosity. And with throttle points, we were talking about the fact that if you reduce the cross-section of your flow, you're also going to have an increase in velocity, but also a decrease in pressure. So with a throttle point, you can manage to decrease your pressure, and you can increase the velocity of your flow by letting it go through a narrower section of whether it's in a valve or whether it's going through a too small pipe for a small section in the system or something. And the problem is that with regards to cavitation is you're going to have a very high velocity coming out of the throttle point and also a low pressure, and those two combined can create these cavitation bubbles, which basically are gas bubbles that form inside the fluid, and then they collapse in on themselves, creating enormous amounts of energy. So I'm guessing that if any of you manage to come up with a way that we can harness that cavitation energy, you would probably get a Nobel Prize. It's pretty easy to create those bubbles, so it wouldn't be a problem getting that stuff on the way. So if you could harness it too, that would have been brilliant. The main problem with the cavitation is that it's going to release the energy, and if the energy is released sort of in the middle of the fluid, it's mostly just going to create heat in the fluid, so it's not that big of a problem. But usually it also gets released, you're going to get a lot of turbulent flow here, so it's going to be pushed towards the walls of whether it's the valve or the pipe or whatever it is, and be releasing the energy in close proximity to the wall, and that's going to damage the material there. So we also looked a little bit, this is a turbine wheel, so we can see just how much the cavitation bubbles have basically just blasted away on the material and just made it completely erode away for some parts of it. And what you can see here is, you can see some of the blades here look fairly good. Then we have some damage on this blade, and on this blade we have a huge amount of damage. So what might have happened in this case, this is a bit different than a throttle point, because here we have the speed and then the angle of the blade that basically creates the cavitation bubbles. But it's the same principle where you have a high fluid velocity and creating a fairly low pressure, and this generates the bubbles. So what might have happened in this situation, for an example, is that if we have a small damage to the side of this blade, it's going to create bubbles in this area, but it's also going to let bubbles fly past it and over to this wheel. And that's probably why this wheel is really damaged, because it's been in the stream of bubbles coming from this one. So you can get sort of a piling on of damage effects with the cavitation. When we're talking about the hydraulic fluids, we talked about using a viscosity index. And the viscosity index itself is fairly easy to use. You usually have tables where you can look at it. But we'll talk a little bit about what viscosity is, which is basically how well the liquid is flowing. So how well you can pour it. If you have it in a cup and you want to pour it out of the cup, if it's If it's of very high viscosity, it will be like syrup or honey, so that it's going to be very slow in being poured out of it, and it's going to be almost hanging in a long drop before it hits wherever you're pouring it to. While if it's water, it's just going to splash all over the place when you try to pour it. So water is very pourable, and honey or syrup is very little pourable in that regards. So one way of figuring out the viscosity of a fluid is to use a system like this, where you fill up this sort of test tube with the fluid, and you have this ball inside it. And then when you turn it around this axis, so you just flip it 180 degrees so that the ball ends up at the top, then the ball is going to slowly slide down the tube, and it's basically the speed of the ball that tells you what the viscosity is going to be. So then you'll have some tables where you can calculate what the viscosity is going to be. So this, of course, has quite a lot to do with the system that we're using, what kind of fluid we are going to use. With a higher temperature, the viscosity decreases, the liquid becomes more pourable. You can see this also with honey and syrup, for that matter. If you heat it, if you pour it into a kettle and you start heating it, it's going to be thinner and thinner and thinner, and it's going to be almost like water in the end before it starts boiling. And it's the same the other way around. If you start lowering the temperature, it's going to get thicker and thicker and thicker until it's almost solid. So if you go too far down on the temperature scale, it's going to be almost solid. With water, it's a bit different, because water doesn't really change the viscosity that much, going from frozen to steam. So we can't really see the effect using water, but as soon as you use something with a higher viscosity than water, you can start looking at this effect when you're changing the temperature. So it's can be very evident in hydraulic fluids that you use. We were also going to be able to calculate flow from displacement volume and rotational speed. And this is either with regards to a pump delivering flow to our system, but we can also do it the reverse way and say that if we have a particular flow and we know the displacement volume of a hydraulic motor, what is the rotational speed going to be? So that you can calculate it that way also, basically just flip it around. And the calculation is very simple, because we have the flow rate, which is the volume per minute or per second. We could just say volume per unit time if we want to be very general on it. We will have the rotational speed n, and we also have the displacement volume itself. So the amount of volume of liquid that we are going to pass through the pump or hydraulic motor per rotation. And then when we multiply it with the amount of rotations, we're going to get the flow rate. So if it was a hydraulic motor and you wanted to figure out the rotational speed for it, you would just do Q divided by V, and you'd get the rotational speed instead. So the example that we looked at quite early in our second, I think it was our second lecture or something like that, we looked at a gear pump where we had 1,450 rotations per minute, RPM, and we had a displacement volume of 2.8 cubic centimeters. And this is often the problem, because we're often given it in cubic centimeters. It would have been so much easier if they just gave it directly in cubic decimeters, so that we could transfer it directly to liters. So we have the revolutions per minute, and this one, even though it doesn't say so, it's per revolution, but a revolution doesn't have a unit, so we don't have it. We have no way of writing it in there. So we put it into our formula, where we get the 1,450 per minute. So divide by minute on that one for RPM, multiplied with the 2.8 cubic centimeters. That gives us 4,060 cubic centimeters per minute in this calculation. But we usually want to have our flow in liters per minute. It makes a bit more sense to us. We know how much 1 liter of milk is, so that makes it more easy for us to sort of visualize how much fluid is passing through here. So we need to convert the cubic centimeters to cubic decimeters instead. And since it's 1 decimeter is 10 centimeters, so if you just cube that, you get 1,000 instead. So you have to divide it by 1,000 to get the cubic decimeters. And that can be transferred directly to liters per minute. So that's a bit easier to visualize. If we know that every minute we have 4 cartons of milk passing through this system, it's a bit easier to know what effect that's going to have on your tank and your reservoir in the system. We looked at determining the differential pressure in a pressure filter. And then we need a overall differential pressure. So you remember the pressure filter, that's not the filter that's on the return line, on the return to the tank. The pressure filter is actually after the pump. So we have a pressure difference across it. So in this case, we had a viscosity of 30 cubic millimeters per second. So this is the kinematic viscosity. That's usually the one we use. We had a flow rate of 15 liters per minute and also a filtration degree of 10 micrometers. So particles smaller than 10 micrometers were allowed to pass through the filter. So in order to figure out the overall differential pressure, we need to do the differential pressure of the housing itself. So the fact that we are changing the cross-section of the flow when it's going through the filter housing, that's going to have an effect on the pressure. We're also going to have a viscosity factor in there, and we're also going to have a pressure differential going across the filter element itself. So we need to combine all of these to see what we're up against. So for the housing, we'll look at that one first. We had a flow rate, liters per minute here. So we had 15 liters per minute. We go up to the characteristic curve for this particular filter housing. So this means that if we're going to do a calculation like this, we have to have the catalog from the supplier of the filter. We need to know exactly what filter it is so that we can get these charts from them. And as we can see here, we're at 0.25 or 0.3, 0.25 we put in here. And then we want to look at the pressure drop across the element itself. And the element has the filtration degree of 10 micrometers. So we need to figure out which of the characteristic curves do we need to look at. 10 micrometers, so that red curve. And we also had a flow rate of 15 liters per minute. So we go to 15 liters per minute, up to the 10 micrometer mark, and over here. So we had 0.8 bars in a pressure difference there. So the last one is the F, the viscosity factor. I'll try to figure out that one. And for the viscosity factor, we have the kinematic viscosity over here. So square millimeters per second. We had 30, so we go and find the 31. And here again, like with the housing, we have only one characteristic curve on this chart. So we can go directly up to that one, and we see we have a little bit more than 1, so approximately 1.2 in the factor for this one. So this is directly just reading off the charts in order to get these values. And then we do the calculation, 0.25 bars for delta P housing, the 1.2 in the viscosity factor, and the 0.8 over the filtration element, 0.8 bars. And we get 1.21 bars in a total pressure difference across the filter. So if we have 20 bars of pressure going from the pump into the filter, we're just going to have 18.8 approximately coming out of the filter. So it's going to affect the overall pressure in a system. So the operating pressure is going to be affected by a filtration element like this. And one thing we need to keep in mind with something like this is that the filtration element, it's going to start getting clogged up as it progresses in time. So the older the filtration element gets, the more clogged up it's going to be. So over time, it might actually get a higher differential pressure in it. So because it's basically going to the particles that are larger than 10 micrometers are going to basically just get stuck in the filtration element, and they're going to, as enough of them start getting stuck in the filtration element, they're going to start blocking some of the flow. So that's just what happens when it gets older and older. That's the main reason why you have to why you should change the oil filter on your car every time you change the oil, because the filter has started getting very dirty, so you get less flow going through it. So it's the same for hydraulic systems. You want to change the filter at regular intervals to make sure that you have a good enough flow through it. We've also looked at accumulators, 3 different kinds of accumulators: piston, diaphragm, and bladder. If I remember correctly, it's a diaphragm that's in the lab, either diaphragm or bladder. I can't quite remember which it was. It's a bladder? Yeah. So then it's a bladder accumulator that's in the lab. And they look more or less like this, if we do a cross-section through them. So the piston one usually either has a massive spring that pushes against the piston, or it has basically just loads of mass on top of it that's going to push it down. So that as you fill in fluid under pressure here, it's going to push the piston upwards. And then depending on if it's a very powerful spring or if it's a lump weight basically on top of it, it's going to be pushed down. If it's a lump weight, you use gravity, so it has to push it down. If it's a spring, you could potentially have it horizontally or something and have it push in, but the springs are usually not that good in these cases, so it's often a bit better to just have this weight on top of it to push it down. And that's going to, of course, give you a certain force that you are going to expel from the accumulator when you need it in your system. So basically a battery of hydraulic energy where you can store pressure while your pump is working, and in case of, for an example, an electrical cutout, so you lose electric supply to your system, the pump stops working, you will still have some amounts of hydraulic energy left inside your accumulator, so that you could potentially perform a set of actions to sort of reset your system and get it to a point where it's not going to be dangerous to just leave it there. For an example, if you have a production line or something like that, you can have enough energy to sort of get all of the processes stopped before something bad happens. It's the same with the diaphragm and the bladder one. They have quite a lot less capacity than what the piston has. The piston can basically just be scaled up to quite large volumes, so you can get enormous amounts of fluid flow from a piston accumulator. While with the diaphragm and the bladder, they are naturally locked in with the fact that they're using gas under pressure to expand, to create the force that you need to expel the hydraulic fluid afterwards. And that also means that they have certain limitations with regard to how much gas you can put in there and how much pressure you can put it under, because they come under the pressure vessel law or regulations. And as the guy at the PRS space was talking about with this 4,000 meter test facility they had, this huge blue tank, just when they had, was it 1 bar or something in pressure difference in there, and they got a small opening, it moved 0.5 meter just because of expelling all of that air that had been, or that gas that had been compressed with just one bar inside. So thinking about the 400 bars they put it under when they're going down to 4,000 meters and simulating that, if something should break then, it would basically just be a cannon shooting straight through all of the walls and all of the equipment, so it would be a massive disaster. Of course, that's probably not going to happen. They have pretty hefty security procedures to go through when they're using it. But the same could potentially happen with a bladder or diaphragm. If you scaled it up large enough, and had a high enough pressure in it. So that's one of the main reasons why they are a lot smaller. But also, like the diaphragm itself sets a couple of limitations to size, just how it's going to be physically able to give the correct function. The bladder is a little bit better in scaling up, but still comes under the pressure stuff there. So we had a couple of values to think about when we were talking about accumulators. Usually we have what's called a transport pressure, and then we're talking about mainly about the diaphragm and the bladder, because we're talking about the pressure of the gas inside them. With the piston, you could have gas inside it, but usually you have something a little bit else, some weight or something on it. But on the gas side, you have pressure during transport, up to 10 bars usually. And then you have what's called a pre-loading pressure, where you fill the accumulator with only gas, and it's usually 10% less than the smallest working pressure of the system, because if you have 100 bars operating pressure in your system, and you want to be able to fill this one up, if you have 101 bars inside your bladder, your hydraulic fluid isn't going to be able to push in, so it's not going to be able to compress it. So you have to have it a little bit less than the operating pressure of the system in order to make it work. And then we have what's called the smallest working pressure, and that's the smallest working pressure in the system, which you either can calculate or you can just read it from one of your pressure gauges if you're running your system. And then you have the largest working pressure, which is set at the point where a pressure relief valve is going to open, or you have calculated what's going to be the largest working pressure. And one thing to think about with the diaphragm and the bladder is that you're going to have gas being diffused through the diaphragm or through the bladder and into your hydraulic fluid. It's going to be a very small amount that's diffused at a time, but it's going to mean that over time your gas pressure is going to be lowered. So it needs to be checked at regular intervals just to make sure that you still have the correct preloading pressure, which means that you have to empty the accumulator of hydraulic fluid and then check the pressure of the gas. Yeah? Diffusion is basically that the molecules of the gas, they basically migrate through the atomic structure of the bladder or the diaphragm. So they slowly but surely move through it, just as if it would be a filter, basically. So we're talking down at the atomic level when they're diffusing through. So it's sort of the same principle that's used in some of the water purification systems, where they are actually, by using pressure, they are forcing the water molecules through a filtration device, which is basically just solid. It won't let any particles through it, only the water molecules. So it's the same that happens here, that the gas can sort of slowly but surely trickle through molecule by molecule. So after a while, you lose some of your pressure. So most likely, it's never the gas that goes through won't be accumulating enough in the hydraulic fluid for it to be a problem, because it's usually going to be following the hydraulic fluid around until it ends up in your tank, and then it's going to diffuse out of the hydraulic fluid in your tank. We've looked at single acting cylinders. We also did the 2 weeks ago with or 1.5 weeks ago, we did the did the log splitter, where we used a single acting cylinder. And the one we looked at in the lecture, when we looked at it, was this one, where we had the bottom of the cylinder here. We had the vent screw in order to be able to release trapped air if that was a problem. We had the piston rod itself, the barrel of the cylinder on the outside here. We had the guide for the piston rod. So between the piston rod and the guide, there is just a very small clearance, diametrical clearance. So it's going to be literally guiding the piston rod. So by having this length over here with the very small clearance, it means that the piston rod doesn't really have doesn't have room to move around while it's moving forwards. So it can only go in a straight line. We also have a seal between the guide and the piston rod in order to prevent dirt coming in here. And we have a wiper here, which also prevents dirt coming in. So with a single acting cylinder, it is only the piston side of the cylinder which is pressurized. So the way we operate them is by allowing pressure inside here, which will extend the piston rod. And then depending on how we've set up our system, if we have a spring attached to it, or if we're extending it vertically upwards, we can use gravity to pull it back. So the only way to pull it back really is to allow all of the pressurized fluid to escape from the piston side of the cylinder. So in the piston chamber, we open up with a return to tank. So all of the fluid will just return to tank, and then either gravity or a spring-based system or something else is going to force the rod back into the cylinder. So this means that we can only perform work in one direction. So we can have work done to our cylinder in order to reset it, but the only way that we can actively perform work with it is by adding hydraulic fluid under pressure into the piston chamber. And that's going to push it in one direction, and coming back, that's not work being done by us or our system, it's work being done to our system instead. So it's basically the same principle as when we're looking at work in thermodynamics, with being done by the system or being done to the system. Yes, I think I'll just quickly pass through these so that we don't run out of time. That was basically just what I've talked about. We have different types of single-acting cylinders. So we have the regular with a piston and a regular rod. That's usually the kind that's used with a spring return, because then you have room between the cylinder rod and the barrel of the cylinder. There's going to be room between here to have a steel spring inside there. Then you have the plunger type, which is this one, where you definitely have to use it vertically and have gravity push it back down, or something else in your system is pushing against it, so that as soon as you release your pressure, it's going to be pushed back in. And then you have the telescopic ones that can sort of extend pretty far in one direction. Just like you can pull out a telescope to become longer, you can also extend those cylinders. So the plunger type is the typical one that's used, for an example, on when you're lifting a car. So with a regular jack that you use, hydraulic jack, to lift up your car, to change your tires or whatever it is, you have some of them that are vertical, where it's directly the plunger that's pushing on your car and lifting it. Some of them have horizontal ones, and then they have a sort of lever system that's going to lift the car. But even though it's horizontal, the lever system is in direct contact with the car, and as soon as you release pressure from the piston chamber, then it's going to be pushed down by the lever system. So it's going to be returned to its original position. And with the telescopic ones, we of course have larger strokes that are possible, because it's going to extend further than It can be longer than just the length of your piston rod because you have several stages that's going to be extending. And this one was a plunger, of course. We also looked at double-acting cylinders, where we have a more or less the same structure, cylinder bottom, barrel, we have a piston, but now the rod is a lot thinner so that we have room for fluid on this side also. And you remember that we can pressurize both sides of this one, so that when we're extending it, we pressurize the piston chamber, pushing it outwards. When we want it back, we pressurize the piston rod chamber, pushing it backwards. But of course, in order to get it backwards, we also have to open up return to tank on that side, or else they're just going to stop. With these, we can perform work in both directions, and depending a little bit on what kind of a double-acting cylinder we have, I'll just go through these. Depending on what kind of double-acting cylinder we have, we're going to get different. We might get different forces coming in different directions. So this one, for an example, it's going to have the full area of the piston. So the full area over here is going to be affected by the pressure. So our force will be equal to pressure times the full piston diameter area, so over there. But if we go to the other side here, we have the entire piston rod that's basically just in the way, so we can't get access to that part of the area. So when we're going in from this side, we need to do the full area, but we have to subtract the area of the piston rod, which means that we get less force when we are pulling it backwards. So pushing is going to give us a set amount of force, and pulling is going to give us less force. And then you have different kinds of designs that are used. For an example, you can have a piston rod that goes all the way through. That way you have the same area on both sides, which means that you're going to get the same force. You're also going to get the same speed. With this one, where we have different areas, we are going to get a different amount of speed. So it's going to be slower to push it out, but quicker to pull it in, simply because the amount of volume that needs to be filled on this side is a lot less because of the piston rod is sort of stealing a lot of our volume. So on this side, we have the full volume to fill in, while on this side, we have the volume minus the volume of the piston rod. So it's a lot less to fill in, which means that at the same flow rate, we're going to fill up this volume a lot quicker than on the other side. Also, something that is used a lot with cylinders is what's called end position cushioning, which basically just means that, we'll just take a look at this one again. If we apply full pressure on this side, pushing it outwards, it's basically going to slam into the end there, unless we do something about that. If we manually reduce the flow rate right before it hits the end, that's going to help, so that it's going to reduce its velocity before it slams into the end there. But if we do nothing, it's basically just going to smack into it, and it's over time that's not good for your cylinder. It's going to damage it over time. So that's why we have something called end position cushioning. And what the end position cushioning does is that it basically blocks off parts of the area that we have here. So that in this case, if it's moved a little bit further to this side, we'll get area both on the piston, but we'll also get access to this, the end of this rod. So that's going to give us, in combination, the full area of the piston, giving us full force over here. When we're pulling it backwards, as soon as this end hits this opening and starts filling up this space, we're going to have quite a lot less of the area. So it's basically, it has a much harder time pushing out. When it's over here, it pushes out all of the fluid through here. And when it hits, this one starts blocking off here, everything has to pass through this area where we have a throttle point, so that we get a lot lower flow going out of it. So basically just we have a built-in throttle point to reduce the flow rate so that we reduce the speed as it nears the end. So then instead of having it slam into the end, we just have it tapping the end, so sort of gently at the end there. The same happens on this side, only it's a little bit differently shaped because of having the entire piston rod going through there. The shape here is just having a slightly thicker section of the piston rod at the end, so that it's going to block off the opening between the piston rod and the guide as it reaches the end there. So we decelerate the high stroke speed, so even though the piston is moving very quickly outwards, it's going to decelerate as it hits those last couple of millimeters or centimeters, depending on how it's designed. So then it's going to slow down at the end so that it doesn't hit it all that hard. So you avoid the hard impacts. And this depends a bit on the velocity of your cylinder. So if it's less than 0.1 meters per second, you don't really need any cushioning. If it's less than 0.3 meters per second, you want this sort of flow control cushioning on it. And if it's more than 0.3 meters per second, then you would want some special equipment in there in order to help with the cushioning. So the book doesn't really go into talking about how the special equipment is, but it's just nice for you to know that there is actually a limit where you need to think about special measures. If you should find yourself in a design situation where you have a cylinder with a higher stroke speed than 0.3 meters per second, you are probably already in dialogue with a supplier, and they're going to tell you all about what you need, so that they're basically just going to educate you on what special measurements are going to be needed there. Because it depends a bit on what designs they're using and their own solutions. So we talked a little bit about how it works. So we'll look at how to dimension a cylinder with regards to resistance against buckling. We also did this for the log splitter. Then we managed to stay precisely within our stroke length on that one. What we did with the log splitter was just use this table in order to fill in what we needed. So this table would, of course, be dependent on what kind of steel the piston rod has been made of. So if it's a very, very strong kind of steel, it would look probably a lot different from this one. What's also been done here is that they've included a 2.5 safety factor, just to make it all ready so that you can just read off the length. You don't need to calculate the safety factor afterwards. And the way we use it is that we see how the amount of force that we're going to get from our cylinder. For an example, with the log splitter, we were looking at 50 kilonewtons. And then you go over to see which dimension you're going to need in order to get down to the correct length that you need. So for an example, if we have 50 kilonewtons and we needed a full meter of stroke length for it, we would have to go way over to the side here. Let's see, a full meter up here. See if I can follow it. So approximately 40 millimeters in diameter for the piston rod. So you would need a fairly thick piston rod for that one if you needed that long of a stroke and that much force on it. And if you can use a chart like this, usually you would get it from the manufacturer of the cylinder that you intend to use. Then this is the quickest way of dimensioning your cylinder. However, if you're talking to a supplier and maybe you have to custom design something, maybe your design is such that you maybe have to build a cylinder into your own equipment, which means that you're basically going to have to recreate the design of the cylinder inside your own equipment. You can't just buy a ready-made cylinder and fit it inside. Yeah? What? Buckling is when you have a rod and you apply force to both ends of it. And if the force becomes enough, it's going to start basically just bending. So you get the same effect as if you applied force to the side of it. So you sort of get a bending momentum, but it is because it's being pushed from the ends instead. So it's a little bit different calculation than what you would get from a bending momentum. So that's why they've given it another name, basically to sort of distinguish them a little bit. So if you need to calculate this on your own, it's the very same way that we would calculate it if we were basically creating a steel support, a vertical steel support that was going to have a lot of weight on top of it. We do it in accordance with Euler, one of his formulas. Let's see, I had some extra here before it. We have this one where we have a permissible force. Exactly why they call it K in this one, I'm not quite sure, but it's the permissible force, so the amount of force that you can allow from each end of your rod in order to avoid it starting to buckle, so that it will still go in a straight line if you apply this amount of force. And you have pi squared, which is easy to put into account. You have the modulus of elasticity. I think I had them here at least, yeah. So you have the modulus of elasticity, which is 210 gigapascals for steel. You have the area moment in millimeters to the fourth power. And that would just be directly calculated from the diameter of your rod in this case. Then you have what's called the free buckling length. We'll look a little bit into that afterwards. And of course, you need to add the safety factor. So with this diagram, they used 2.5. At least it said so in the book. And usually it's between 2.5 and 3.5 as a safety factor for those. So you can put it up like that, and you're going to get the amount of force that you can have. So if you then put in, if you say for an example that you need a length of 1 meter in stroke length, as we looked at here, but you would prefer having 28 millimeters in diameter. So if you put all of this in here, you would end up with up to 28 there, so somewhere between 10 and 20 kilonewtons. You wouldn't be able to reach the 50 kilonewtons that you needed. And of course, you can turn this one around and use the area moment to figure out what the diameter is supposed to be. So then we'll look a little bit at what's called the free buckling length. And in the book, there are 4 cases that they list up, but the 2 cases that were supposed to be here are generally not good to use. So I just dropped them on this one. And what it depends on, really, is how you've mounted your rod. So this also counts if you're using a steel rod to hold up the roof of a building, for an example. So if that concrete pillar there, if that had been made of steel instead, basically you do get the same calculation with concrete, only a bit different. But if that had been made of steel, you would have had to make this calculation, and you would have had a sort of locked in, what's it called? Securely clamped is what they call it here, in both ends for that one, because it's securely clamped to the floor and it's securely clamped to the roof. In this case, it would be securely clamped to the floor, but it's pushing something straight up, so that's just swaying up there. And that means that the free buckling length would be 2 times the stroke length of the cylinder. And that has to do with the fact that down here it's pretty much following the vertical curve until it gets up here, and then it starts swaying off. So if you had sort of tried to recreate this shape on this one, you would have ended up getting twice the length before you got back into a locked-in position. So if you flip it around, it's going to be twice. But what's usually done when you're using cylinders is that you usually have hinges on them. That's at least what I've seen the most of, is that you use a hinged system in both ends. And that means that you get a free buckling length that is the same length as your rod, so the same length as your cylinder then. So that's what you're going to have to look at when you're looking at it for a calculation directly. And these kinds of setups, you can find a lot of it in the Blue Book, the Mechanical and Metal Trades Handbook. Often then just for regular steel rods that are clamped or hinged or different solutions done to them, and they're going to tell you what the buckling length is going to be. But you can transfer it easily to a hydraulic cylinder by just thinking like this instead. We'll do a 15-minute break before we continue on with the cylinders. Yeah?
Anyway, you don't have to go back.
Yeah.
On this, regarding the buckling, so on the second
Right, so we'll continue on then. I can see I really need to pick up the pace a little bit if I'm going to get through everything, but I'm thinking this is the stuff that it's the longest since we did, so it's more important for me to summarize this, because the rest should be fairly fresh in your memory, since it's the longer into this lecture I get, the closer to today we get in the lecture, so it's the older stuff first. So just to sum up how we do when we're going to select a cylinder for a specific task. We're going to have to figure out what force we require from our cylinder. In the log splitter example, we looked at we needed a 5-ton force because we were going to basically duplicate the log splitter that you could buy from a store, and it delivered a 5-ton force. And when you know what kind of force you want from your cylinder, you need to figure out what operating pressure you're going to have in your system, because force equals pressure times area. So you need to know what pressure you're going to have, and you need to know what the diameter of the piston is going to be. And very likely, at least if you're designing a system totally from scratch, none of these would be set beforehand. So the diameter of your piston will be dependent on the operating pressure, and the operating pressure is dependent on the whole rest of the system. So to first off, when you're beginning on your system, you probably just have to set what you believe is going to be the operating pressure in the end. You might very well have to change that later on in your design. That's also why your design process is happening on paper to begin with. You're not really buying stuff to begin with. So, for an example, if you had set an operating pressure of 100 bars, and then later on you figured out that you're going to have 200 bars instead, you haven't already bought your cylinder for 100 bar pressure. It's not been bought already. You're still working on your paper, or on your computer for that matter. So it's not going to be a huge problem in changing stuff. You just need to go back and redo your calculation for the diameter of the piston, because now you have to change the diameter of your cylinder because you have a higher pressure. So that's one thing that you have to keep in mind. Either that, or you have to put in a pressure reducing valve so that you still get 100 bars going into your cylinder. And then we need to know what speed is required of the cylinder. Sometimes you don't really have any information about what speed you're going to need, so then what's going to be nice to use then are the general speed requirements for end position cushioning. If you want a simpler, cheaper cylinder, you're going to go for a speed of less than 0.1 meters per second, because then you don't need end position cushioning. And if you go for between 0.1 and 0.3, you're going to have to need a bit more expensive cylinder. So that has a little bit to do with that. And in order to determine the speed, you also need to know the flow rate. Do you have to put in a flow control valve in order to control the flow rate going into your cylinder? You need to think about the surface area ratio. So the area on the piston side and the area on the piston rod side. What is the ratio between those? Because that ratio is going to directly affect the speed when it's being extended and then when it's being retracted. It's going to have different speeds on those two if the ratio is something different than 1. You're also going to have to look at what is the required stroke length. So how far does the cylinder need to extend itself in order to perform the task it's supposed to perform. And then you need to think about the diameter of the piston rod so that you have enough resistance against buckling, that it's not going to buckle. And basically, if it starts buckling when you're using it, you're going to bend it out of shape and you're not going to be able to use the cylinder anymore afterwards. So that's the summary of what you need to think about when you're designing, when you're selecting a cylinder for your design. Then we're going to quickly go a little bit through the motor again, how we select the motors. Of course, we can do calculations with regards to what amount of rotational speed we need, with regards to the flow rate we have, or if we need a particular amount of rotational speed, for an example, 400 RPMs, then we can calculate how much flow rate we're going to need, just using switching around a little bit on the one that we calculated for the pump, because it's basically the same. But we could also use, if we know the particular motor that we're going to use, like this one, an OMR 125 from Danfoss, we can use a graphic like this to figure it out, where we have areas that give us the efficiency, so 83%, 80%, 75%, 70, and 60 on this one. So we can look at what efficiency we're going to have from it. We can look at what amount of power we're going to get from it. We have 1, 2, 4, 6, 10 kilowatts, 12 kilowatts even. And we can also see pressures on these lines. We can see flow rates on these lines. And we have RPMs down here, and we have the momentum going up here. So just finding sort of the correct area in here that's going to give you approximately the correct value on everything can tell you what your system needs to be. So for an example, if you need a specific amount of RPMs, the 400 for an example, and you also need a specific momentum, so then we do at 400 here, we go straight up. If we have 160 in momentum, we go over there, that's approximately here. We can see that the pressure line going through there, that's 100 bars. So that means we have to deliver 100 bars into our motor in order to gain 400 RPMs at 160 Newton meters. Also, when we're over here, we are going to have approximately between 6.5 and 7 kilowatts of power going out of this one. So that means that we have to take into account the amount of power that we're going to have going out of the motor. We also need to look at it's within the 75% efficiency range. So that means that we need the power that we are getting out, those 6.5 kilowatts, they are just 75% of the power going into the motor. So we need to calculate how much we are going to deliver into it. So that's sort of, we can figure out a lot of the values that we need in our system by setting a couple that we need, and then we can figure out the rest by looking at the chart and seeing where we are in relation to the other values. Yeah, this is just the one we did in the calculation, where we were looking at an efficiency of 80%, a flow rate of 30 to 40 liters per minute, a pressure of 60 to 80 bars. That left us in this area, which meant that we have somewhere between 120 and 220 Newton meters to choose from, and somewhere between 230 and 320 RPMs to choose from, because then we are inside this green part here. Actuating force. So now we're moving over to valves, looking at those. So the actuating force is the force needed in order to move the valve, basically. So if you have a Poppet valve where the flow is going in the same along the same axis as the slide, basically, on the valve, the piston, then you will have a very high actuating force when you are pushing against it, like this. But if you need to open it using a lower force, you can allow some of the fluid to escape and get to the back of it using a pilot channel. And that means that you will have some of the force counteracting it on the backside there, so you need less force in order to keep it in place. And when we're talking about the actuation force here, we are talking about the amount of force that we need to apply up here in order to push it down and close off the valve, in this case. So without the pilot part, we have to counteract all of the force from the pressure in the flow. And if we have this pilot part up here, we are getting some help from the pressure, so that we don't need to push all that hard on it. We'll look a little bit at poppet valves and slide valves and how they work. So I already mentioned poppet valves being as having the flow going along the same axis as the piston, whereas with the slide valves, the flow is coming normal to the axis instead, so at a 90-degree angle to the axis of the piston. So the piston is basically just sliding back and forth in order to open up different channels inside the housing, which is also why it's called a slide valve. Just quickly doing the pros and cons for them. The pros for a poppet valve is that it's leak-free when it's closed. You don't have any leak coming through it. So there won't be, when it's closed like this, there is no fluid escaping past it. You need a higher actuation force because you need to counter some of the pressure. Even though you have the pilot system, you still need to counter some of the pressure in the flow. So you need a lot more force than with a slide valve. They also have the disadvantage of not being able to have complex designs within them. They are a very simple design, and if you need complex functions in them, you need to use several poppet valves in combination. So you need to combine a lot of poppet valves in order to get a very complex function from it. With a slide valve, you don't have full closure, so you do get a little bit of leakage going along the slide, basically. So it can both leak into the leakage area where you usually have a leakage line going back to the tank to catch all of that fluid, and you also have some small trickle going into your components. But the slide valves, they don't require all that much force to move, so they are much easier to move back and forth in comparison to the poppet valves. And they can also create pretty intricate designs, allowing you to have several switching positions and have many ports, so that you can have, for example, 6 ports going out of it to different components. 1 port coming in with pressure, 1 port going out to the tank, and 4 ports going to different components if you need to. And you can also have quite a lot of switching positions and a lot of functions between those switching positions. And the switching overlap and the control edges, that affects the positions of the slide valve quite a bit, where we have the possibility of having a positive overlap, which basically means that you have to slide you have to move the slide a lot further before it actually opens up, because you have that overlap going there, so you have to make sure that it moves all the way over before it opens up. If you have 0 overlap, as soon as you start moving it, it's going to allow flow past. And if you have negative overlap, it's allowing flow past if it's in the mid position. So then the flow is just going to go straight past it. It's only when you move it to one of the sides that it's actually going to block the flow. And these edges of the slide, they can be shaped in different ways. You can have a sharp edge, like shown up here. The sort of disadvantage with the sharp edge is, it's both a disadvantage and a positive side with them, is that they abruptly close off the flow. The disadvantage is that you can get sort of shocks going through your system, because you are so quickly closing off the flow that the rest of the hydraulic fluid moving towards the valve, it sort of gets crushed together, almost as a chain collision going on there. So you get a shock moving through your system. But on the other hand, it reacts very quickly so that you get a sort of instant reaction when you close off a valve like that. So for an example, for an emergency brake to stop a hydraulic system, where you basically just have a push button that you can hit if something happens, as soon as you hit that one, if you have a sharp control edge, it's going to instantly shut off the system and shut off the flow. So you're going to get this shock going through your system, but you've still stopped it immediately. But in order to, yeah? The shock will usually can create pressure peaks, basically. But the main problem with the shocks is that you get vibrations moving through your system. So through your hoses, through your pipes, and through their couplings. And this leads to if this happens very often, it can lead to fatigue stress in those components, which can lead to them breaking in the end. So you don't want it happening often, but for an example, for an emergency stop, they are very useful to have. If you don't want these shocks moving through your system, you can have a chamfered edge or a notched edge, which will basically allow a trickle of flow moving through before it fully closes off. So it closes off most of the flow, but a little bit is allowed through until it is fully closed. So you have this possibility of doing it a bit more gradually than just an abrupt shut-off. Then we'll try to look at both pressure relief and pressure reducing. I've gotten the impression that some of you have a little bit of difficulty differencing these two. So I'll try to make it a bit more clear now by doing them both at once here. So a pressure relief valve. The point of that one is to take care of, for an example, pressure peaks. So if you suddenly get a pressure peak in your system, whether it is a cylinder that's connected to something else and that other part suddenly jerks on the piston rod and creates extra force moving in, so basically just trying to compress the hydraulic fluid, or if it's a spike in the electric current to the motor, and the electric motor gets suddenly increases its rotational speed a little bit, which will again increase the pump rotational speed a little bit so that it outputs a higher pressure. Any kinds of stuff like this that increases the pressure above the normal operating pressure, you would want a pressure relief valve in. And what happens is that it's connected to the pressure side of your system, and that has, in this case, an adjustable spring so that you can set it to a particular pressure. Let us say, for an example, 150 bars in this system. And it will stay closed so long as your pressure is below 150 bars. But if you suddenly get a pressure peak, 160 bars maybe, then it's going to open because the spring isn't strong enough to resist the force of the pressure. So it's going to open up and release some of the fluid back to the tank. And as soon as enough fluid has been released back to the tank for the pressure to reduce to 100 bars again, it's going to snap shut so that your pressure stays at 100 bars. And you can see this is a poppet valve designed for this one. You can have them as slide valves also. And the way we, I'll do that afterwards because I get both of the symbols up afterwards. The pressure reducing valve is a little bit different because it gets the pressure in on one side and it moves through the entire valve. But then just as it is about to exit, we have this pilot channel that leads it over to this side. And if the pressure becomes too high before it exits the valve, so if it's supposed to release pressure at 120 bars there, and it's getting 140 bars in here, then that difference in pressure means that it's going through the pilot channel over here, and it has enough pressure on this side to counteract the spring, so it's closing off the valve. And that means that it's closing off a little bit of the flow. It's basically throttling the flow there. And when you throttle a flow, you get a pressure reduction. So that means that as soon as it has throttled the flow enough for the pressure here to go back to 120 bars, then the force on this side isn't strong enough to counteract the spring, so the spring pushes it back and you get full flow through it again. So with this one, you're interested in releasing fluid back to your tank when you have too high of a pressure. And with this one, you're interested in restricting fluid flow in order to keep your pressure at a certain level when it's going into your components. For an example, if you have a pump that can deliver more pressure than what you need to your components, that's when you want a pressure reducing valve. Because then the pressure reducing valve will get the full pressure from the pump coming in, and it's going to reduce it to the correct level going out to the components. And the way we differentiate them is when we put these symbols beside each other. And you can see the symbols are fairly similar to each other. The main difference is that for the pressure relief valve, which is this one, the line shows that it is closed. We don't have a direct connection between pressure and tank. And it's only going to open up when we get enough pilot pressure there. That's when it opens up. While with the pressure reducing valve, we have a constant opening from pressure to component at all times, but we have the possibility of getting too high of a pressure in the pilot line, and then it's going to push it away so that it closes off. It closes off the connection between P and A on that one. So that's the main way of looking at it. Is the pilot line connected to the entrance on the valve, or is it connected to the exit of the valve, basically? That's how you differentiate them. So we'll look a little bit at directional control valve designs. I'll just do one of the examples that I did during the main lecture there, where we're looking at a directly actuated, because it has a hand lever here, two-way valve. And the first two, that's the one that's actually connected to the way. So it's a two-way valve. That's the first two, and then way. And that means it has two ports, basically. So it has two ways for the flow to move from the valve. And the second two here, which is behind the slash there, means that it has two positions to stay in. So it can either be closed, as it's shown here, or it can be open, allowing flow past it. And it also has the hand lever, of course, on this one, and it has a detent that's going to keep it in the position that you leave it in. It doesn't have a spring that returns it. And for this one, we have a shut-off function, so it's meant to be able to either allow flow through it or shut it off. And the way we can look at it is like a two-lane road, where we have a pressure on one side of the road and the component on the other side. And once it's shut off, both sides have a red light, so there is no traffic moving along this road at all. And once we activate the hand lever, we are opening it up so that we get the green light in both directions, and we can have full traffic moving along the road. So basically full flow going through the valve. And if we activate the hand lever again, we are closing it off so that it's completely closed. And this, you can sort of move off to more ports, more switching positions, and more functions in all of it. But it is the basic principle on all of them. You have the switching position that tells you where the traffic is moving, and you have the amount of ports that tells you where they are heading. Is it coming from the pump? Is it heading to the tank? Is it heading to one end of the cylinder or the other end of the cylinder? Or whatever is happening in that valve. We'll look a little bit at solenoid actuation, which is basically just electrically controlled valves, where the solenoid is a sort of a copper ring here with electrically conductive material. So you have basically loads of copper wire that's been set into a spiral pattern here, filling up a lot of area in here. Once you set electricity going through that copper wire, it's going to generate a magnetic field, and the magnetic field will move stuff in a particular direction. So any magnetic materials will be moved in a particular direction. And you have the armature in the middle here that is magnetic, and it's going to be moved towards the springs over here. So it's going to push on the springs. If you put electrical energy into the copper wires up here. And you also have the possibility of sending it the other way if you want to by changing the direction of the electric current, stuff like that. So you're basically controlling it using magnets, electromagnets. And then we're going to look at the connection between the transitional positions and overlap. So we looked at overlap and control edges a little bit earlier. And now we'll look at what overlap means to our transitional positions. So if we have a positive overlap, we will have between two positions in a valve when we're switching. It has this dashed line on that box in the middle, which means that it's only when the slide is moving that this function is in play. So when the slide is at rest in one position, it's either going to be this or that one. But as soon as it's moving, when you're activating the solenoid or if you're pushing the lever or whatever it is, as soon as you're moving it, it's going to have this effect. And with a positive overlap, it means that it's going to shut off all of the ports. So they're going to be shut down while the slide is moving. But if you have a negative overlap, where you actually have a clearing when it's in the middle, you're going to end up having a full opening while you're moving the slide. So it means that you're going to have both your pump, your pressure port, and your both of the ports going to the component, and also the port going to the tank. Everything is connected, so you have full flow going through it. So this means that on the upper one, where everything is closed when you're moving the slide, it means that if you're activating a cylinder, it's going to keep the pressure inside the cylinder because it shuts off the ports going to the cylinder. So it's basically just locking the fluid inside the cylinder. But if you have a negative overlap, it gets a full opening with return to tank. So it means that you're actually losing a little bit of the pressure. So depending on how quickly you're moving the slide over to the opposite switching position, you can potentially lose quite a lot of pressure. So if it's a hand lever and you're just slowly pushing it over, then you're going to lose quite a lot of pressure before it hits the other switching position. If it's a solenoid, we're talking about milliseconds before it hits the other side, so you're probably not even going to be able to read off a pressure difference on a pressure gauge. But with a hand lever and moving it slowly, you would really see the effects of this. And for valves with 3 positions, we usually have a mid position, and often they are centered by springs so that they're going to return to this mid position if we don't activate anything. So one of the switching positions that we can have in the center is just allowing flow to go directly from the pump and back to the tank. And this means that our pump is basically running with 0 pressure when we're not operating this valve, because there is almost no resistance. The only resistance that we're getting is when it's pushing the fluid through the filters. So depending on how much of a pressure differential we have going through the filters, we're going to have a little bit of pressure, most likely a couple of bars or something as it's moving the liquid around, but nothing like an operating pressure of 220 bars or anything like that. One of the positive things with this is that if it's going to remain in this position for long stretches of time, so that for an example, every 15 minutes you're going to switch it over to one of the sides and keep it there for a couple of minutes, and then you're going to let it go back into the middle position. It means that the pump is not going to be running at full speed at all times. So the pump has having very little resistance. It's not getting any particular amounts of wear and tear either when it's running directly back to tank. So it's a very beneficial position for the pump when it's running constantly. And it also means that you are constantly moving your fluid through your filters, so that you are making sure that your fluid stays clean at all times. So it's a very good thing to have. So if this is the case with a 15 minutes start rest in this position every now and then, you could potentially have a slightly smaller filter pack, because you don't really need to move all of your fluid through it at all times. You couldn't run a bypass filter or something like that. So it's a possibility of reducing the filtration in the system, basically, because you're constantly running it through it without sending it into components that are going to add contamination particles to it. The second one, all ports are closed. So of course, in the case of the pump in here, it's just going to have full pressure, because it's just pushing against the wall, basically. So it has, if the operating pressure is 220 bars, we will have 220 bars pushing against this one then. Oops. For the third one, we have a full connection between everything. So that means that we get pressure to the tank, and we get pressure going to our components and everything. So we basically have zero resistance in our entire system. So if you have a cylinder moving, it's going to be completely loose, so that you can go over to it and you can just pull on the piston rod and pull it in and out if you want to. It's not a problem, because it doesn't have any resistance in the fluid. All of the fluid is just returning back to tank and slowly getting filled up, and so it's not a problem moving it about. The same with this one. The pump is shut off, but all of the fluid is returning to tank. So with this one, you are potentially, if the tank is at a lower level than your cylinder, you are potentially draining your cylinder completely of your fluid. So you could end up getting air bubbles in your system this way. So because you are sort of letting everything just follow the path of gravity back into the tank. But you could also have the tank closed off and the pump connected to both of the ports. So in the case of the cylinder, that means that you would have equal pressure on both sides of your piston. So depending on the surface area that you have, it's going to, if the ratio between the surface area is something different than 1, so that you have a more area that it can hit on one side, on the piston side, then it's going to extend, because it has more force going that way. But depending on the system you have, it might be beneficial actually to have full force going to both sides of it. If it was a hydraulic motor, it would get basically force coming in both directions, so it wouldn't rotate, so it would just stop there. Then we'll look very quickly at a detent, so how the system is built up in order to keep the position of the valve. And we'll zoom in there a little bit and see that there are grooves cut in the slide rod over here. And then we have balls, just like in a ball bearing there, and we have so the ball bearing part, and then we have some sort of elastic element, whether it is a ring that is made out of some rubber-like material, or if it's some sort of steel spring that is a radial steel spring. It might be quite a lot of different ways of doing this, but at least it has the possibility of being expanded a little bit. So that if we start pulling on the rod, the part in the middle here will force the balls to be expanded outwards, and thus also expanding the elastic ring, until we hit this groove over here, so that they're going to just snap back into that groove and keep that position. So it means that we have a certain amount of force that we need to overcome before we can manage to move the slide. So we'll do the non-return valves also before we shut off. So with non-return valves, we allow flow to go in one direction. So if we have flow coming from this side, it's just going to add force into the poppet and just push it more into the sealing surface. So we're just going to basically make it even more shut than it already was. But if we get flow coming from the other direction, and if the pressure is great enough to counteract the spring, then it's just going to push the poppet open and pass straight through it. And this is the sort of basic symbol that is used if you have a spring. You can also have them just without a spring. Then you usually don't have a cone in there. It's just a ball that's lying in there. And the ball is just lying in there, quite literally. So it's just going to be moved around inside there by the fluid. But as soon as you push the fluid in the wrong direction, it's going to hit the sealing surfaces and close off completely. You can also have them pilot operated. So that means if we get force coming from the B side here, it's just going to push on the ball valve and not get anywhere. It's just going to add to the force from the spring. This is the symbol we have for it, where we have this pilot line coming in to the underside of the check valve, basically. If we have flow coming from A here, it will pass straight through because it will just push on the poppet part, the ball, and open it up. But if we have flow coming from B and we also have pilot pressure coming in here, pushing on this rod, then the rod opens up the ball. So it's just going to push open the ball, and then you can allow flow from B to A instead. So that's one way of using a non-return valve and then forcing it to open up when you want it to open up by applying some pilot pressure to it. So that's one possibility. I think we'll have to stop there. Of course, I'll make the whole presentation available so that you can look through the last couple of slides once I've gotten the video up and running. I just want to give a quick message with regards to office times. I have my own exam coming up also, so I'm going to be working quite a lot on that one next week. So I won't be all that much available in the office next week and the week after, the first couple of days there, because it's the 1st of December that I have my due date on the exam. It's a home exam, so I have to write quite a large piece of paper, 4,000 words or something like that. So, so I deliver that one